So welcome back, everyone. The announcements for today are those of you who didn't pick up your exam in lecture on Wednesday or Friday or drop by my office to get it already, the exams are with the TAs now, so you can pick it up in your recitation this week. Also, you probably want to do that sooner rather than later because regrades are due 10 a.m. Wednesday. So if you want me to look at regrading any part of your exam, as a reminder, the procedure for that is staple a piece of paper on the front saying what you want looked at and why, and I'll go through all of them once the deadline passes, which is Wednesday, 10 a.m. Okay, questions about any of that? Cool. Alrighty. So lecture was a little small on Friday before break, which is understandable, but if you weren't here, please make sure you go through and watch the lecture capture because we covered two pretty important reactions. We covered organometallics and we covered carbenes and carbenoids. So that's all going to be fair game for stuff on the exam, on the final. Okay, so my plan for today is wrap up the last bit of chapter 9 and then we can start 10 on Wednesday. Okay, so one more reaction from chapter 9 that we're going to do is radical halogenation. Okay, so we've seen radical halogenation before, sort of. We saw radical HX addition, radical HBr addition of alkenes. This one's a little bit different, but it still has a lot of similarities. So radical halogenation of alkanes, not alkenes. We're not starting with a double bond. Okay, so here, instead of adding something to an alkene, we're going to pull off an H and replace it with either Cl or Br. Like in a lot of other cases, those two halogens are kind of in a sweet spot for this reaction energy-wise. F is too reactive. I guess it does do this reaction, but you have very little control over making it stop after it pulls off one H, and it's just going to like tear through the molecule and do a bunch of this, which is usually not very useful. And iodine is not reactive enough. Okay, so just like the other radical reaction we've seen, we can split the steps into 3 parts. So initiation, propagation, termination. So let's take a look at that. Okay, so this is a little bit different from when we did it with alkenes. If you remember, when we got started on alkenes, we took a peroxide, like an ROOR, split that in half in the middle, and that was how we got our unpaired electrons. What we're doing here is actually just taking a dihalogen, like BR-BR. And you may remember, I sort of mentioned this as another option when we looked at alkenes. If we hit this with UV light, which is often written as H-nu, or you can write UV light on the arrow too. What we're doing is pumping enough energy into this system that we're going to break the bond, but neither bromine wants to give up the electrons entirely. So we're going to do a bond breakage like this where each atom gets 1 electron out of there. Do you guys remember the descriptor for that? Yeah. Homolytic, yeah, I think I heard a couple of people say it. Okay. So I split bromine into 2 radicals, and that's it. That's actually the only radical we need to do, so that's our initiation done. Okay, so next up is propagation. So I'm going to show it happening to this specific molecule for reasons that I'll get into later. Okay, so it turns out that the most substituted H is going to be the best place to do this. So what happens is the Br dot that we just made comes in, rips an H off, and the arrow pushing for this looks really similar to how it did when we were doing stuff with alkenes. Bromine brings in 1 electron for the new bond. The other electron has to come from the CH breaking, and then the leftover electron falls back onto whatever the rest of the molecule is. Okay, so that gets us that. and that generates a waste molecule of HBr. And then the radical that we've just created goes on and does the same thing, chips in one electron to a bond, the Br-Br bond brings the other electron, and then the leftover stays with the other bromine atom. Okay, so like that. Okay, and then like always, termination is just a mismatch of various different stuff happening from radicals sticking together. So that could look like maybe two Br dots getting back together. Or maybe Br dot and molecule dot getting together, which happens to give us the same product as the major product of propagation up here. Or it could be two copies of the molecule get together, which is sometimes a little tricky to draw, but it's easier if you mirror one and then stick it onto the other. So that's another case of termination. Okay. So here's the mechanism. It's pretty similar to what we've seen before. It's just instead of breaking a pi bond on the molecule when we get started, we're actually breaking a sigma bond, which is why we can manage to get away with doing this on alkanes. Okay, so any questions about the mechanism so far? Okay. Yeah.
Would, for propagation, a radical that was created in initiation ever be used in the same step?
Well, I guess propagation, kind of the key thing is that it's always just like one radical does something and makes a new radical, and then that does something and makes a new radical. So it's always like one radical in, one radical out, kind of. But yeah, like it could get involved with another Br dot, but that would be a termination example. Yeah. Yeah, and it's just more likely statistically that only one radical is going to be around in any place at a time, just because like radicals are pretty sparse compared to everything else. So, okay, awesome. So now let's look at a few different kind of consequences of the way this works. Okay, so I mentioned up here that it works for bromine and chlorine. F is 2 reactive, I is 2 unreactive. But it actually, there's still a noticeable energy difference between bromine and chlorine. So bromine is pretty endothermic when it does this reaction. So that means that bromine has to sort of scrimp and save its energy before it can even manage to do this at all on the molecule, is how you might want to think of it. And so it has to be a lot pickier about where it does this reaction. So it's pretty selective. And it really prefers to go for the most substituted H. So that's why I chose this particular molecule, because it's got an actual tertiary H on there. So tertiary is going to get replaced much faster than secondary, is going to be much faster than primary or methyl. So in other words, if you take this same molecule again and hit it with Br2 and H nu, just writing it all together on the arrow there, you're going to get this, the same thing that we showed up here, just drawn a little differently, as the only major product. You might get like a small percent of molecules where like maybe an H got pulled off here and replaced, or maybe off of here, or maybe off of here. But those are going to be like sub 1% usually compared to the most substituted product, which is the bromine replacing a tertiary H. Okay, so bromine's real picky just because it can't afford to be kind of wasteful with its energy in this reaction. By contrast, chlorine is pretty close to energy neutral. It's still slightly endothermic. And it can pretty much go wherever. So it does still have a slight preference, like tertiary is still faster than secondary, is still faster than primary, but that's largely balanced out by the fact that in most molecules you actually have a lot more primary H's than you do secondary H's, and you have a lot more secondary than you do tertiary. So like looking at this guy, for example, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 primaries. We got 2 secondary H's, and we've only got 1 tertiary H. And so those, like just sheer force of numbers, kind of balances out with how much faster tertiary is. So it's usually pretty close to an equal distribution for chlorine. So if we take the same molecule and hit it with Cl2 NH nu, we're going to get not just the tertiary H getting replaced, we'll also get secondary or this primary or that primary. So all of those are going to be major products. So all of these are getting formed in significant amounts. I have to make sure I keep a space there between in and significant, otherwise that changes things. Okay, so chlorine is kind of a wild card. It's just going to replace an H wherever. So this is usually not a super useful reaction, at least on this particular molecule. The only time that chlorine is going to be like useful for doing this sort of thing is when all of your H's in the molecule turn out to give you the same product. So for example, if we took cyclohexane and hit it with Cl2 H nu, the only thing we're going to get is just chlorocyclohexane. Okay, so this would be useful, but most other molecules, there's different options, and so chlorine's kind of a mess. But bromine is still nice and predictable. Okay, one other thing that's worth pointing out here is this is all assuming that the reaction only happens once to each molecule. You are going to get some cases where you actually replace 2 or maybe 3 H's per molecule, but you can mostly get around that just by being careful about how much halogen you add. So if this comes up on an exam, for example, you'll notice a lot of the time, or the textbook problems will say, like, assume only monohalogenation products. Okay, so realistically, that might not be a perfect assumption, but we can get pretty close based on how we set up the reaction. Okay, any questions about that? Okay, cool. So that was actually the last reaction from Chapter 9. Give yourselves a pat on the back, you made it. So the rest of this chapter, we're not done quite yet, because what we're going to look at now is something that involves taking everything we've seen so far in the course and sort of stacking it together to achieve sort of more complicated goals. So this is the first example that we're going to see. of multistep synthesis. Okay, so the general idea here is that a lot of the time we'll say, I'm going to draw it over here, I need a final product, otherwise known as a target material, or TM. And this might be something that we want to make because we happen to know that it has properties that we find extremely useful. Like maybe your final product happens to be something that people know kills a certain type of cancer cell, or maybe it makes a certain type of liquid crystal or polymer or something. It's just some molecule that we want to build. So a lot of the time we'll give people a starting material or SM, and we'll say, okay, take this thing, turn it into your final product using any reaction that works, or any reaction that we've covered in lecture a lot of the time. A lot of the time, you can't get there in one step with one single reaction. So we're going to have to go through one or more synthetic intermediates. Note that these are not the same as mechanism intermediates. If you remember there, intermediates in a mechanism are like you've done half the arrow pushing and here's how it looks like halfway through that reaction. This is more, I've done one entire reaction with a complete mechanism that gets me to here. This is like the product of that reaction. And then maybe I can have to do another reaction to make a different synthetic intermediate before I can take a third reaction and use that to convert this intermediate into my final product. Okay, so in other words, the product of one reaction has to be used as the starting material for the next reaction, has to be used as the starting material for the next reaction. So we're kind of stringing together multiple different reactions that we've covered already. Okay, so now that we've covered some reactions that make alkyl halides, so like all of this chapter, or actually we've covered reactions that use alkyl halides as a starting material, which is all of this chapter, and we've covered some reactions that also make alkyl halides out of alkenes in chapters 4 and 5. So we can start sort of using one product as the starting material for another reaction. Okay, so let's start doing some examples. What if I give you this molecule and I say, actually, I want this instead. I want that bromine 1 carbon over from where it is now. Okay. Sometimes that'll just be given as like a synthesize this product from that product. Sometimes I'll do like a question mark over the top. But in other words, it'll say synthesis or synthetic somewhere in the problem usually is how you'll know we're asking you to do this. Okay, so we don't know any way to directly pull a halogen off of one carbon and stick it onto a neighboring carbon, right? But we do know a way to get rid of a halogen, make an alkene, and then we can add stuff into the alkene at whichever site we want, because we know how to pick between Markovnikov and anti-Markovnikov addition now. So a lot of the time if you see this like try to walk a functional group over by one carbon kind of a deal, what you're going to want to do is, and a lot of the time we'll draw it as like this string of one or more intermediates like going along between underneath, kind of connecting them. A lot of the time the obvious way to do that is we have to go through an alkene that looks like that. So we do an elimination, we get an alkene in the right location, and then we can add back in selectively to the alkene and get stuff where we want it on that molecule. Okay, so that's kind of the general idea is like we got to have control over what happens where. Okay, so we also need to make sure that we're forming the alkene in the correct location. When I do this elimination, am I doing the Zaitsev or the anti-Zaitsev product? Anti-Zaitsev, right? So what kind of base would I want to use for that? Tert butoxide, yeah. Okay, a few different ways of writing that, but tert butoxide or TBUO minus, or however you want to show it. If you want, you can include a solvent, but you don't have to. Okay, so just as a note here, must be anti-Zaitsev. Okay, and now we've got an alkene in the correct location. When we add into it, do we want it to be Markovnikov or anti-Markovnikov? Anti-Markovnikov, so what am I going to use for that? Yep, HBr and peroxides, yep. Okay, so for this particular example, we have control over where the alkene forms. We can pick anti-Zaitsev. And we have control over where the halogen adds afterwards. So it's got to be anti-Markovnikov for that step. Okay. So, questions about this example? Okay, cool. So you'll notice that a lot of these examples involve like shuffling a halogen around. That's just because a lot of the reactions that we've seen so far happen to involve halogens or alkenes in some combination. This is going to get expanded more and more the more reactions that we cover. But this is the kind of stuff we've got in our, as you might hear called synthetic toolkit for now, is like eliminations and then additions. Okay, so what if we try to go a different example? Which is, what if we try to go the other way around? Nope. Yeah, so if it's a synthesis, you do not have to show the mechanism for any of these. Just write in the reagents that you use for each step and also like the synthetic intermediates. Yeah, and actually that's another thing I wanted to remind you guys of or tell you guys about is that usually on a synthesis problem, about half the points are tied to just getting a reasonable chain of synthetic intermediates. So if you know, okay, I don't remember any of the reagents, but I know I'm going to have to go through this alkene, that's probably going to be about half the points for the problem. And then getting the reagents on the arrows correct is going to be about the other half. So just knowing that, okay, this is something that can be done, hell if I remember how, but this would be the synthetic intermediate to use, is sort of a big part of getting the problem solved. A question in the back? Or stretching? Ah, okay. Okay. So what if I'm trying to go the other direction, where I start with the less substituted halogen, and I make them more substituted? Okay. So, in this case, the intermediate is actually going to be exactly the same alkene. So I'm just trying to eliminate, make a double bond, and then add selectively back into the double bond. Okay, so am I trying to do the elimination Zaitsev or anti-Zaitsev? Or does it matter here? Yeah, it's meaningless distinction because there's only one possible elimination I could do. So what if I tried using, say, ETO minus as my base? That would do the elimination, but what side reaction am I going to have to worry about here? Not acid-base, but so I've got a primary alkyl halide. I got a strong base, good nucleophile. What's going to happen? Yeah, SN2. So that's something else we got to be aware of, is just because the elimination happens to be looking easy and favorable doesn't mean that elimination is the only thing that's going to go on here. So again, if I want to force elimination, tert butoxide. Okay, so I got primary alkyl halide, I got strong base, poor nucleophile, That's going to give me an E2-SN2 mix probably, but I can tip that towards just E2 if I use slightly higher temperatures. I don't remember if I mentioned temperature in here in the notes. I think I just say TBU. But yeah, if you want to really give this thing a nudge in the right direction, a little bit of heat might help too. Okay, so so I do my elimination with tert butoxide. There's only one location for it to go, and I've hopefully successfully avoided SN2. Now I need to add back into the alkene. Am I doing this Markovnikov or anti-Markovnikov? Markovnikov, yep. So I'm just going to use HBr for that. And that should get me the product that I want. Okay. So questions about those two? Yeah. So in the notes I leave it off. So that's actually sort of another big picture good question about synthesis, which is like how favorable does each of these steps have to be? So like if you get a mixture of products, do what you can to like tip it so that the product that you want is actually like the one being formed as the major product. But yeah, sometimes there just is no good way to do that, and sometimes you're like, okay, this step is going to give me like the thing I want plus a bunch of other crap. Well, I'll just have to clean those up during like a separation after I do the reaction, so like extraction or distillation or something to clean it up afterwards. Yeah, so in the lab, usually you'll do one reaction, you'll clean it up so that the molecule you want is the only thing you have, and then you'll take that, do the next reaction, clean it up. And so a lot of the time there's a whole bunch of purification steps in between like each step of the actual synthesis. Yeah. Okay, so like the higher the yield you can get on each step, the better, but sometimes there's just no great workaround. Okay, good questions. So any other questions about these two examples before we move on to something more complicated? Okay, awesome. So, a third example. Okay, so two things about this. One is we have never directly added an OAC onto the molecule, so we're going to have to figure something out there. And the other is, where the heck do we even start with this one? Like, it's got nothing on it right now. Fortunately, we now have a reaction that we can use to start with just a bare alkane and get at least some sort of, as we would say, synthetic handle on there, so that we can do something to it. Even if it's not like in the right place or exactly what we wanted, at least having some halogen on there will give us some way to start working with the thing. Okay, so if you're ever given a bare alkane for the molecule here, pretty much your first step is going to have to be radical halogenation. Okay, do I want to use bromine or chlorine here? Bromine, yep. And that is because if I used chlorine, I would get a random mixture of Cl adding here versus adding here. Or it could add here or here, but those are the same as these two sides. So, okay, so bromine is going to be more selective. Just going to get this as my major product. Okay. This is now looking pretty much the same as that first example that I put up there, where I have one functional group at the end of the chain, or I have one functional group one away from the end, and I want to get a functional group at the end. So let's do that whole eliminate, then add in to walk things over by one carbon. All right, so pretty much copying from up there, tert butoxide gives me the alkene. So I don't have any good way to add an OAC group directly to the alkene. But bromine, as it turns out, is a pretty convenient placeholder atom. So I'm just going to say, okay, I'm going to focus on getting just anything in the position where I want it to be. And then because we know how to do substitution, we can swap that group out later. So let's get just bromine on as our sort of placeholder atom for the time being. So in other words, let's make sure we get the right regiochemistry, and then we can worry about the particular functional group. Okay, so we got the bromine on there, and then swapping that out for any other group, as long as that other group, OAC minus, you might remember looks like this, or you can go sort of look up what that looks like, but this is going to be a weak base and a poor nucleophile. And we've got a primary alkyl halide here. So yeah, SN2 is probably going to be kind of slow, but at least it'll probably be the major product. Okay, so pretty much all we need to do is say OAC minus as the base nucleophile here to come in and swap out for the bromine. If you want, you can be more specific and say like some kind of counter ion. In the notes, I say like NaOAC. And then if you want, you can also use a solvent that's going to help SN2 a little bit. So like polar aprotic. I think I say acetone in the notes. But yeah, just that'll help with the SN2 a little bit, although it won't make a huge difference. Okay, so the core of this one is pretty much the same as up here. We have something on one carbon. We need to bump it over to the next carbon. And then there's just a little bit of getting that set up at the start and then switching the group out right at the end. Sort of another big picture thing about synthesis is sometimes you might not know how to do the first step, but sometimes you can sort of piece together a little bit of the synthesis from one end and a little bit from the other, and then you can maybe like figure out one more step and one more step, and then as long as you can sort of get the two paths to meet up in the middle, then you've got a complete pathway going from your starting material to your product. So don't think that you always have to sit down and be like, okay, step one would be this, then step two would be that. Like sometimes you're like, I have no idea, but look at this product. The thing right before that must have been an alkyl halide, because that's pretty much the only thing I know how to substitute for. And then you can work your way backwards from there. So it's pretty nonlinear solving these problems, especially once we get more and more reactions under our belts. Okay, so I'm going to go erase the other side of the board if you guys want to take a minute. Okay. Okay, so let's do one more example. So here's an alkene. And I would like to make this molecule instead. Okay, so those of you who are here the Friday before break or who have watched the lecture capture have got a leg up on this one. So I'm trying to make a cyclopropane here. Pretty much the only starting material that I know how to make that from is going to look like what? Yep, well, so a carbene is the reaction, or is like what I generate during the reaction, but the starting material for that, like what do I stick the carbene onto when I'm doing this? It's going to look like this, right? It's an alkene. All right, so again, I don't really know how to start this particular one necessarily. I mean, I do, but I might not if I looked at this at the start. But I do know there's pretty much only one possible way to finish this reaction up, and that is if I'm going to do this cyclopropane reaction, I have to have had an alkene there beforehand for that to work. Okay, so then the question is, how do I get from here over to there? This is kind of looking like that walk a functional group over by one carbon deal that we did before, only now it's not a functional group that's like a halogen or anything, it's an alkene. So I'm going to do sort of like the flip of what I did over here. Instead of going alkyl halide to alkene to different alkyl halide, I'm going to go alkene to alkyl halide. And again, bromine is a really convenient placeholder. That's kind of my default, like stick something on there so that you can like eliminate it, get it off easier later on. But I'm going to add something onto one of these carbons and then do an elimination later on to get the alkene where I wanted it. Okay, so I'm going to take this. What reagents do I want for the first reaction? HBr, yep. Could I use HBr and peroxides here? Yep, yeah, I could do that because neither side is more or less substituted than the other. But I can also get away with not doing it, so let's do that. Less to write, and if you're doing this in the lab, less to actually add to the reaction. Okay, so HBr, when I'm doing the elimination, this is actually exactly the same as the first example's first step. So that's tert-butoxide to do the E2 elimination anti-Zaitsev. And then the reagents for this one, this is what we covered just before break, but this is going to be Simmons-Smith cyclopropanation. So CH2I2, zinc, copper, and THF is the most common way to see that. Okay. All right, so any questions about this sort of combo of stuff? Okay, cool. So the last thing I'm going to cover here is sort of a few conventions that you might see as far as like figuring this out. Because a lot of these are short enough you can sort of look at them and be like, okay, well, I almost right away like know what the synthetic intermediates are going to be. Sometimes it's not so clear-cut, especially when we have like this gargantuan molecule that maybe like your research group and 3 other research groups around the country are collaborating on, and you're like, okay, you make this quarter of it, and we'll make this quarter, and then we can meet up and like stick them together, and hopefully it works. So one sort of way of thinking for picking these things apart from the starting material is called a retrosynthetic arrow or retrosynthetic analysis. So this is just sort of a more formal way of what we already did a little bit of, which is start at the product that you want, the target material, and work backwards. Okay, that's where the name comes from. Retro means like backwards or in reverse. and synthetic is synthesis. Okay, so the convention for how to show this is retrosynthetic arrows. Which is this full-headed but double bar arrow. So this pointing towards, say, the right is the same as a regular arrow pointing to the left. So in other words, this means can be made from. Or is synthesized from, is how I have it in the notes. Okay, so in other words, say the second example that I have over there. Bromine on the last carbon. Oh, actually, this is a new example. So how do I get from bromine on the end to bromine in the middle carbon? Could also be written as, how do I make a molecule with bromine on the middle carbon? Well, it can be made from bromine on the end carbon. Okay. So you might see it either way around. This way of thinking is just easier when you have a target material in mind. A lot of the synthesis problems, what we'll see, especially the further on we move in the course, won't even give you a starting material. They'll just say, for instance, make this molecule, and then they'll give you some limits on what you can start with, because if they didn't, you could just say, go buy that molecule from Sigma Aldrich. But a lot of the time they'll say, like, make this from any molecules of fewer than 6 carbons, for example. It would have to be like a bigger, more complicated molecule. And so then you can pretty much like start with whatever target material you're told to make, and then just start picking it apart and say like, okay, I know I could stick this chunk on during a reaction and this other chunk on during this other reaction. And then you just keep like breaking it down until you've got a whole bunch of chunks that are all under the carbon limit and go about it that way. Or if you're doing this in an actual lab, it's just you have to make this from stuff that you can buy commercially, and that's not too expensive, basically. So you can just sort of say, all right, I'm going to start with this big complicated molecule that I want. I can stick this chunk on, and oh, look, I can buy that chunk commercially, so I don't have to make it. And then how about the rest of it? I can figure out how to piece it together from other stuff that I can buy, and then sort of build it up that way. Okay. All right, so keeping track of all this, because like there's a ton of reactions that we've covered already, and there's a ton more that we're going to cover. How much time do I have? Okay, good. So keeping track, there's actually Appendix 5 in Loudon is super handy here. It lists a whole bunch of different what are called functional group interconversions. And also where you can find those reactions in the book. So you can go through and see like, okay, what are some ways to make an alkyl halide? That's from a chapter that we've covered. That's from a chapter that we covered. We haven't done that one yet, so I can skip it. And just sort of keep track of like, okay, do I know all the ways that I could make this functional group if I had to do it that way during a synthesis? So super handy to keep it organized. Another thing that will be really useful for studying is if you work on, say, putting these functional group maps together from your own notes and memory. So say I want to make this molecule. I could just draw a whole bunch of arrows like pointing into the center and say, okay, so I know I could make this from maybe this, which would be a Markovnikov style addition, which means I could use something that adds Markovnikov. Probably wouldn't want to use acid catalyzed hydration because that might rearrange on me, but I'm not going to write out the whole set of reagents because we're short on time, but oxymercuration would do that. Or I could do it from a different alkene and do anti-Zaitsev, which would be hydroboration oxidation. And get to there. Or I now know that I can swap out a halogen pretty easily for numerous other functional groups. So I can get there just by reacting this with either H2O or OH minus, depending on if I want to do this as a SN1 or SN2. Actually, SN2 would be better here. This would probably give rearrangement now that I look at it, so I might have to update that in my notes. Okay, so that's kind of one way of keeping it straight. One more tool that's going to help you here is the disconnect line. I've sort of informally drawn this in a couple of reactions already. So we've seen this in ozonolysis. If you remember, I showed like sort of chopping through the alkene. And the way that we formally show like a little cut here line, which may as well be like a dotted line with scissors on it, is we do a line with a couple of little knobs on either end. Okay, so I think in the notes I don't include reagents. I'll just update this for DMS specifically. But so that's sort of a disconnect of that's where the bonds are going to break during this reaction. We could also do it as, if we're trying to get a bromine off the molecule entirely, we could show a cut here line across that carbon-bromine bond. If you want it to be a little bit more explicit here, you would also at the same time have to show the H getting lopped off as well. Okay, so we have sort of a small set of synthetic tools in our toolkit right now. We're going to be adding more and more to that as we go along, but it really helps to practice not just individual reactions, but also like get a lot of practice at stringing them together to accomplish your goals. So exam archives and then the textbook has more and more synthesis problems as we go along too.